Well, so I'm going to talk about the miniature student satellite, which I have spent 10 years of my life as a retired person on. And so it started in January 2015. Took a few years to get up to speed. And now we're approaching, hopefully, the final stretch. So the idea behind my presentation is to show that how you could use a practical project to learn about space technology, and what I've tried to do in that respect during the MIST project. It's nothing earth-shaking. It's just straightforward, but I think you may find it interesting anyway. So yeah, I graduated from engineering physics in 1969, so it was a while ago. That was before mobile phones, before the internet, before computers. Yeah, it was a long time ago. But complex analysis is the same as it is now. So anyway, so the idea behind the MIST project, the miniature student satellite, is the students should participate in the entire process of system design, testing, launch and operation of a real satellite, not just a paper one. And so students can work towards credits or as volunteers. And also do degree projects. We had many of those in the beginning of the project, but right now we're sort of in the test phase, and the design is more or less is finished. So thesis projects are more suitable for design work, because then you create something new. Now you just test it to see that it works. Anyway, the satellite looks like this. I'll describe it in more detail later. So it's divided into three stacks: top, middle, bottom stack, and the middle stack is called the subsystem stack. We'll return to this. The goal is to launch MIST next year because we have a frequency allocation that expires at the end of next year, and we have to get the satellite into orbit before then. So the technical details. Well, MIST is a 3-unit CubeSat. The CubeSat was a concept invented, well, I guess almost 20 years ago. And there were sort of 1-liter units. That's why it's called a 3-unit CubeSat. It's 3 liters big, 10 by 10 by 30 centimeters. And they use, space electronics weigh roughly the same density as water. So it means it weighs roughly 3 kilograms. And actually it weighs, 3.3, so it's pretty close. So the satellite has then, subsystems, of course. Even a small bird must have a beak, eyes, wings, legs, the internal machinery, and so does a satellite. So it contains subsystems. Attitude control, onboard computer, radio, of course, antennas, an electrical system. And then it has some useful cargo, called experiments in this case. And these kind of satellites are, they may create space debris once they're used, so that the altitude is less than about 550 kilometers, I mean. So you get rid of them after 5 years. Anyway, so here you can see how big it is. This is the Mach satellite, which is, test mounted in the thermal vacuum tank at Albanova. So you see, you can hold it in your hands easily. Well, the experiments on the satellite are several. This is from the physics department. It's called CUBES. You can read about it on the web. It's for X-ray detection. These are scintillators. You can see the yellow ones. There are 2 of these units on board. Generates most of the data from the satellite. This is 2 experiments. On the left is a silicon carbide, Carl Michael's contribution, and the one on the left is called LEGS. It's a piezoelectric motor that we got as a gift from a company in Uppsala called Piezo Motor. It's more for fun, but it's interesting. It actually moves in an orbit. And we have a propulsion system. Uses butane as a cold gas propellant, made by a Danish company called Gomspace. They've stopped making it, but we got the last copy. So it's an interesting device. Hopefully we can do some maneuvers in orbit. So So first of all, what is more about the idea behind this? It's not a research project. Education is the purpose. And it's real world technical work. And you'll experience all aspects of a space system. Of course, it varies from phase to phase, but the entire project covers all aspects of a space system. And as usual, when in engineering, there are no textbook solutions. There are some, of course, but in general, you have to think for yourself. So you have to learn to deal with, well, here's the hard stuff: teamwork, complication, compromises, uncertainty, and endless small problems. That's what engineering is all about, solving those things. So this is sort of very educational. This is what real life outside the academy looks like. It's hard. Building space systems that work is hard work. So it's an activity, the MIST project is an activity within the KTH Space Center, which Krista Fuglesang started in 2014. Now I'm the project manager, and it started in 2015. What have we done for 10 years? Worked on it. It's not the same people. They're changing all the time, which means there's difficulty to keep continuity in the project. Knowledge transfer is the big problem, but it's also the purpose that many students could work on these matters and learn. So, in a manner of speaking, you could say that it takes time is part of the idea. So this project was conceived within these two parts of KTH, and we spent, well, it's hard to say exactly, more than 6 million crowns. Funding has come from the Wallenberg Foundation, AFRI, Space Agency, KTH itself, and numerous smaller contributions. We buy all major subsystems except the onboard software, which has been developed by students. It's not an easy task, but it's also very educational. That's where all the everything has to be solved within the onboard software, all the activities on board the satellite. The two main subcontractors is IC Space in the Netherlands and GOM Space in Denmark. So we bought some parts from IC Space and some from GOM Space. They are sort of designed to work together. It's sort of a CubeSat kind of standard. Maybe it's a bit old-fashioned now because it's quite a while since we bought them, but they actually fit together, these units. For example, the power system and the battery comes from GOM Space, and the radio, onboard computer, antennas and stuff come from IC Space in the Netherlands. So what I hope that students will learn is what I call the ethos of engineering. It's a bit preposterous, but anyway, my personal version. So do more with less. It's obvious that's what an engineer does. And attention to detail all the time. Wake up in the middle of the night and think, what should we do about this and that? And assumption is at the root of all mistakes. You have to think. If you assume something is already figured out, probably you should think again. And if it's not tested, it will fail, also known as Murphy's Law. And it is an absolutely immovable law. It's always valid. If it's not tested, you're going to look for trouble. We had an example last week, which we solved on Saturday evening, it turned out. And document what you do, be professional, because the problem is there are many people working on the project, and if you don't document, it's very hard to find the information. If it's in the head of somebody, it's okay, but if you constantly change people, which you do in a big organization, a big company, you have to document what you do. And teamwork in the real world, that's what it's all about. So you don't play schedule games. What I mean by schedule games is that you hide behind somebody else's delay. That's dirty tricks. If you're late, say so. And to paraphrase President John Kennedy, ask not what your coworker can do for you. Ask what you can do for your coworker. Help each other. So idea is sort of a foretaste of work in industry. So the areas where work is being done is, mechanical stuff, thermal analysis, onboard software, ground station, mission operations, attitude control, functional testing, And here's, many skills are needed in these areas. And these are just some examples of that. You see, programming, electronics, control theory, additive control, mechanical design, thermal analysis, CAD, how to use machine tools, 3D printers, materials and processes, radio stuff, vacuum test equipment, and much more. All of that sort of passes by this project. So here's some statistics about the students who've been working on the project. So it's hard to compute exactly how many students have worked because they come and go. But it's about 230 in total over these years. So 40% are Swedish citizens, rest of the European Union 30%, rest of the world 30%, 20% of the participants have been women, and 40 theses on various levels so far. And the study programs that the participants come from are, of course, aerospace engineering and the space track, or also the electromagnetics, fusion, and space engineering track, embedded systems, of course, for onboard software stuff, and the bachelor's courses or program for electronics and computer science. Very useful areas. This is just a graph of the number of students that have been engaged per team, which is a team is a 1 semester thing. We change people each semester. Well, I change it during the semester. But it goes to show how things started out nice and slow and then picked up. And right now it's a lot of people engaged, which means that managing this is a big task. And it is also handled by students. Students manage themselves. It's part of the exercise, how to run things and take responsibility. Some examples of student work. Well, we have something really strange called the office days, and on 4 Saturdays per semester. And it's actually the students' ideas. We sit together on a whole Saturday. Some people come in for a couple of hours, work on a problem. Somebody else comes a little later and work on another problem. There's always somebody there. This was not this past Saturday, but the one before that. It was quite busy. I think there were, around 15 students around on a Saturday. Oh, impressive. So this is some functional testing in the main lab, and you can recognize the man on the right. He sits right there, looking after his experiment. And the shorter guy near the window, he's from Piezo Motor in Uppsala with a little engine and motor that moves back and forth. And William, the software guru, is on the computer. This is a recent picture. The coordinator for the functional testing team, Prerna, and Alvar, one of the students working in the functional testing team. And what you see on the mess on the table is actually the satellite in what we call a flat sat configuration, spread out on the table. We actually communicate with this mess by radio. So the radio is this little black box near the edge of the table. That is instead of the ground station. But just on Saturday evening, we made a test where we actually transmitted from the antenna on the roof into this room. Worked fine. And we did a vibration test on the 28th of January in Kista at the RISE vibration test facility, where we vibrated the bottom stack where most of these KTH-produced experiments are. They are not previously qualified for the flight environment of a Falcon 9 rocket by SpaceX, but the others are. So we ran a separate test of these untested experiments. They survived. That was nice, and they still work. And nothing came loose. Also another major step forward. Yeah, you see here's the black box, is the adapter which you put the satellite in, and this is sort of the thing you put on the vibrator. And you apply the random vibration spectrum supplied by SpaceX for the Falcon 9 rocket. And then you check in between, you do it on the 3 different axes. You check with a sine sweep, a sinusoidal sweep across from up to 2000 hertz to see that nothing has changed. Nothing has come loose. You can hear if it rattles, of course. This went well. Okay, here's another example. We had to build a work platform for the ground station. to work on the roof where we have the antenna, and which because the owner of the house thought the old one wasn't any good, so students had to build one out of steel, stainless steel and stuff. And we just lifted on the roof the other day. Here's Victor and Nasir on their creation. Lots of welding. We got it up the other day on the roof, and now we have to just make it run. That's just another example. Thermal design. This is what we call a cover plate for the for the CUBES experiment. So there's a lot of stuff about what kind of materials you choose and what optical properties these materials, this tape in this case, have. And the optical properties determine a lot about the temperature. That's a whole discipline, the thermal control, a big discipline. Attitude control, another interesting thing. So the satellite is supposed to point to one end down, and it's going to fly in the V direction in this diagram. And so, we need to point within maybe 30 degrees normally towards nadir. And the actuator is magnetic torque coils. You just use the Earth's magnetic field and use electromagnets to steer. Of course, you can't steer in all axes at the same time. So it's not perfectly controllable. It's a rather sloppy control system, but it's good enough for our purposes. And the sensors is analog sun sensors and a 3-axis magnetometer. And the controller is in onboard software. It's a PD regulator. Proportional and derivative, no integrating term. Satellite position, you have to know where you are in space. So it's done by dead reckoning. So what you do is you tell the satellite what the orbital elements are, and then you have a little software loop inside the satellite that uses the time to compute where the satellite is. The satellite uses Unix time, by the way, which starts on the 1st of January 1970. Yeah. So that's the way we do it. So we bought the basic ADCS software from this company in the Netherlands. And simulation done by my students here. Example of a hardware in the loop simulation. I won't go into details, but it was kind of a complicated thing. The student that was responsible for that, he reported for a whole year that it didn't work. Finally, he made it work. And then I gave him this plastic gold medal for suffering the indignity of telling us every day for a whole year, every week, that it didn't work. He now works for the Defense Research Agency in their space department. Well deserved. So this is what the actual simulation this simulation looks like this in real life. So the green box is a laptop, and you have SSS, means sun sensor simulator, etc. IMTQ means the magnetic coil simulator. It's all made by Arduinos, lots of Arduinos simulators. IOBC means onboard computer. I is for IC space, onboard computer. It's just a printed circuit board. This is what the result is when the satellite goes into eclipse. It loses orientation because there's no sun reference, so it wobbles a little bit. Otherwise, it's pointing reasonably well. Thermal analysis, another thing. This video, hope it works, shows the temperature on the satellite. Of course, blue is cold and red is hot as the satellite goes around the Earth. Let's see if we can make this. Yeah, here it goes. It's hot, hotter, hotter. Solar panels, of course, on top are getting warm. Not so strange. That's where the sun impinges. And now it's getting greenish. It's getting colder. And here we go into eclipse, which means into darkness, and that goes cold. By the way, this thing on top there doesn't look exactly like this in the present configuration, but it's close enough. Okay, so I mean, there's a big thermal analysis package made by Airbus that we use in the project, and also in the courses for space technology. Another big thesis was the finite element model of the satellite. which was quite important. We had to be sure that the resonance of the satellite are not too low, because a rocket has a lot of nasty vibrations in the low frequency regime. It's called, when you shower and you turn off the hot water quickly, the pipes vibrate like that. Same thing with rockets. When you turn off the rocket engines, you get that kind of effect. And what happens is the rocket goes up and down like this. It's called pogo. You know, a pogo stick you can jump around with. So it's called pogo. Astronauts used to complain that it was rattling. Same thing with satellites. They get a real shock when the engines are turned off. And there can also be continuous pogo. And that's in the low frequency regime. So the natural frequency of the satellite should be well above that. Otherwise, it will break. So the crux is here. How do you compute how the satellite is mounted? You see 3 different examples here. So that was a whole semester's work for one student. This is another interesting. This is the satellite antenna pattern for the receive and transmit antenna, and of course the reddish part is down. And so we had to reorient the antennas, because the first orientation, the antenna diagram with the red air is pointed up, and it's supposed to point down. So a simple switch, it worked. So this was quite a while, but that was a bachelor thesis job. And by the way, Oscar here, he has got a PhD in antenna theory. Okay, later. As orbital analysis, this is an old computation which is still valid. Lifetime of mist, and NASA and also ESA has a program, software that you can compute how long the satellite will stay in orbit. NASA has called the debris assessment software. And you can plug in what the satellite looks like, and if it's tumbling or stabilized, and its mass, and a typical orbit, and you can compute how long it will last in orbit. And you can see, in this case, which is a typical launch by a Falcon 9 by SpaceX, mist would burn up after 4.3 years. And the end is very abrupt, as you see. Very typical. This is a ground station, and if you look at Technique in 31, you'll see this antenna on top of the building. Right now, it stands still because we have a cabling problem that we have to solve when the weather gets better. We know where the problem is. Yeah, that's what it looks like. And let's see if this thing works. Tracking a satellite across the sky. Speed it up, of course. We're tracking a satellite called FunCube. It doesn't exist any longer. It's burnt up in the atmosphere. You can see this moves very quickly. Because we speed it up. And then the antenna goes to a resting position where the satellite will appear on the next pass. It just goes there and waits. And then as the satellite pops up over the horizon, the computer in the ground station moves the antenna. Why does it move in jerks like that? Well, because the beam width of the antenna is very wide. So you don't have to point it very accurately. You do it when you need it. You can set that angle, how often you're going to move it. So anyway, you may recognize where this. Actually, we're looking straight north in this picture. Oops. This is the mission control and my office. So the control center is in the far end of the room. These are the MIST website. It's called mistsatellite.space. You recognize the lifetime curve there. And some of our sponsors. So try to keep this reasonably updated, but there's other channels. Instagram, for example. Instagram channel, recommended. It will be much more lively soon. And that's all, folks. Thank you. I brought some goodies. Put them over here.
Some different pieces will move around inside. You have some kind of actuator or what that is.
Yeah.
Do you expect that to change the attitude of the satellite?
No, it doesn't weigh much.
Please repeat the question.
Yeah, okay. Yeah, will the piezoelectric motor change the attitude of the satellite? I would be surprised if it did. It doesn't weigh much and it doesn't move much. You have to look really closely to see it move, and it moves very slowly. And it moves back and forth like this often. So it will average out. That would be fun, moving the center of gravity, center of mass, sorry. Yeah, okay. We were quite worried about it when we did the vibration test because it's not built to be launched into space. It's often used in electron microscopes and stuff on the ground. And here we put it in a shaker and really vibrated. It still works. So,
More questions.
go ahead.
The only ground station that we use is the one here at KTH, right?
Uh-huh.
So how do you get the data from satellites when it's not visible in the host?
Stored on board.
It's like double data.
Yeah. So the idea is that we store telemetry on board, and when the satellite comes over the ground station, we just download it. And it's interesting that you mention it because the instrument that generates most of the data, it's the CUBES experiment, and it generates data cover the whole Earth in half a day, 14 hours actually, and then it takes 5 days to download that data because we have a very slow data link to the ground. We could use other stations as well, and that's an idea we'll work on later. But at the moment, we use one station. So the total contact time per day is not much. One pass, the longest pass over KTH is 9 minutes. Normally it's sort of 6 minutes something. 6 minutes, 6 to 9 minutes. It's a very short time, which means that everything has to be done by stored commands. So the satellite is programmed to do things. Nothing, if I can decide, should be transmitted in real time. Should upload all the commands to the satellite and just sit back and relax and enjoy the flight, so to speak, as they say on airliners. And then everything happens automatically, because otherwise people get nervous. 6 minutes, very short time. One keyboard entry wrong and you have to start all over again. So, well, but a backup ground station would be nice. We'll work on it when we have the time. Yeah.
How does one do it?
You talk to me. Simple as that. What we're going to do this semester, I think, is we're going to make, how should I put it, specific recruitment. Earlier, we've just put out the big dragonet, and we'll see what we get. And whoever applies, we try to use. But now we may need some specific talent or knowledge, and we'll start with those, and then we'll find out. Right now, in the spring semester, people get a bit mobile, I say, at graduation and stuff. And it's very hard to know exactly who is finishing when. So it's sort of a transition period. The fall semesters are much quieter because then there's no thesis work around the corner, but the spring semesters are a bit uncertain. So I've spent the last week trying to figure out who's going to leave, and when, and who do we need instead, So, but you may have the perfect, qualifications to do a good job. But we may also find out that we need, general hands just to do the grunt work, making cables, carrying things, testing, measuring, worrying, stuff like that. So, which means what you do in the space project. You work around the clock and worry. That's what you do. Sorry about painting such a bleak picture, but it's also fun. Yeah, go ahead.
Tesla set up many about 9 launcher.
Yep.
Do they actually provide that in some digital format that you can just feed into the machine?
Yeah. Yeah, they provide a table and the graph. So you have to prove that you can survive that. Otherwise, they won't take you on as a passenger. So it's in the manual. You can go to SpaceX's website and download the user's manual for the Falcon 9 rocket. It's there. And they only require random vibration. You don't have to do the horrible sine vibration, or shock, which is really horrible. Shock tests are the scare of space engineers. So because a CubeSat is mounted inside a container, it's called a containerized payload, which is a rather benign environment. If it was sitting on itself by a simple adapter, it would be worrying. So CubeSats get special treatment, actually. Nicer treatment. Yeah.
How close is this to completion?
All the things are ready. Now we have to test them, see that everything works as it should be. So there's nothing more to produce. Of course, we have the ground station right now is the antenna is out of operation, but we know where the problem is. So now it's that phase of the space project where everything has to come together and you have to prove everything. So the next test that we have scheduled is something called the communications and deployment test, where we'll actually simulate the first 4 or 5 hours of the space flight, including deploying the antennas of the satellite, actually doing it, and also using the ground station to communicate with the satellite. So that's scary.
But Sven, we also need the funding for the satellites. So I'll pass the basket around for contributions. No.
Yeah.
No, we're not asking students to pay for this.
No.
We know you can't afford $1 million.
It's actually getting cheaper to launch satellites. It used to be very expensive, but what SpaceX and other big rockets, they provide this group travel, like a charter trip. So, for example, on the SpaceX launches 3 rockets a year called transporter flights. On each of these rockets, there are maybe 100 satellites. So, which means that for them to organize that is tough. So they actually have travel agents, you call them, that handle the interface with the customers. So we are talking to these travel agents, and they provide all the services, transportation, look at all the documents, etc. Yeah. Oh yeah.
Ryanair.
Well, I think CubeSats are sort of cattle class. I mean, they're not the prime because and we get dumped overboard wherever it's suitable. So, pardon? I could call it that, yeah. But I mean, we get at least dumped overboard. Yeah.
Question up there?
Yeah.
Yeah. What will the final launch costs be?
How much it cost?
Yeah.
1 million Swedish crowns. Roughly. For 3.3 kilograms. It used to be much more for a CubeSat. It used to be 3 times as much. And this is because SpaceX has this reusable rocket and they launch it regularly. And they have lots of payloads on the same rocket. That's got the price down. So it's just amazingly cheap compared. But still, to make that rocket is not cheap. I mean, even though it's first stage is reusable, it's not for free. That's for sure.
All right. One last question up there.
Yeah. Have you already discussed how to run the operations, like once it's launched and becoming routine, and the ships and passengers?
Yeah, we spent time on that, and the whole principle of operation is, as I said, stored commands and that you pre-program the satellite. So it does, and we've really thought about how to the work cycle, and we may modify that as we go along. But this is the basic way. I mean, I've been involved in Swedish satellite projects for many years, and this is the way we usually run them, especially those very short passes over the ground station. Sweden's first satellite stayed maybe 5 or 6 hours above the horizon. It was a very elliptical orbit. So you could sit back and just relax. and run it in real time. But with any low orbit satellite, you have to use stored commands and pre-program everything and then just let it happen.
Just for a few years or?
Yeah, but I'll tell you, I'll give you an example of a satellite that we called Astrid 2. It was launched in 1998. It was this big satellite. It was operated by a KTH student during the summer of 1999. And he did nothing, more or less. He had, this was before cell phones, he had these pagers, which was hooked up to the control center. Control center ran automatically with stored command. If there was after a pause, it transmitted a text message to the student, said, this is the number of telemetry formats received, or alarm this, alarm that, alarm this, and he would leave the pub and could take a cab and go to the control center and figure out what the hell was wrong. So you could run it very routine basis. Now, it was quite a nice summer job for this KTH student.
Huge control with 50 people.
No, just one student in a pub with a pager. That was what we had.
Yeah. All right, so thank you for coming. We're gonna shut down. There's a class coming in at 1, but then we'll be around if you want to talk to me.
You